It's my pleasure to invite Professor Panda, who I met in South Africa about 8-9 years ago, invited by Dr. ICICLE, which has been at Multicore World, but unfortunately hasn't been able to be here this time. And well, we were just guest speakers, and one conversation bring to another, and always generous with his time and friendship, so we became friends since then. And as many of you know, I always carry my standard little flyer, so I gave him the flyer number 29 in supercomputing, and he said, I can go this time. Welcome. So you are on. Thank you.
Okay, good afternoon. So thanks, Nicholas, for the introduction. As some of you know, I've been in the high-performance computing almost now for 40 years. That is like I can say that is my 1.0 incarnation. We started with InfiniBand, high-performance networking, MIP's MPI library. Some of you might be using it. Those projects are sustaining. MIP's project, I've been doing it for 23 years. That is like the open source MPI, which is being now used by more than 4,000 organizations. And from just the OSU side, we even crossed like 1.75 million downloads. So then we have moved into like the high performance AI, MPI-driven machine learning, deep learning, big data. So those are the kind of the pure computer science projects, HPC projects have been going on. Now this thing is a very new project. I've been leading for the last 2.5 years. In fact, Nicholas gave a lot of background information, so I'll go into that. Digital agriculture is one of the focus in this one. I'll go into more details. So this is one of the NSF-AI Institutes. How many of you are familiar with this NSF-AI Institutes? Okay, some of you, of course, but not. So over the last 3 years, U.S. National Science Foundation has invested 25 such institutes. Each institute is $20 million for 5 years. So overall, if you can count, a quick math, $500 million. NSF is investing to really push the frontier of the AI to the next level. So each one of these institutes has its own kind of a area or responsibility. So this one is mostly on I'll go into more details, the ICICLE, which is the cyber infrastructure. How do you design the cyber infrastructure? So we have been funded through National Science Foundation. They have the Office of Advanced Cyber Infrastructure. In fact, Manish has done a lot of work on that directorate. So we have been funding through that. And I'll try to introduce you to this institute. And especially within that institute, how we are trying to really help in the digital agriculture field. So that will be the storyline of this presentation. So here, whatever I'll be presenting, this is like I am trying to present on behalf of all the ICICLE members. There's a very large team I'll try to introduce. This is like a photo from our all-hands meeting. So the way I'll try to proceed, I'll start with a high-level ICICLE vision and goals. So what are the research challenges being addressed? And then I'll go into only one kind of the focus, which is the digital agriculture. Then, since our objective here is to actually have cyber infrastructure, one of the agenda or one of the responsibilities given to us is to really make softwares available, not just like published papers. Just like the MPI library, some of you know, we have been releasing that MIP's library continuously for the last 24 years, so that people can actually start building these systems. And that is the way we will try to democratize the AI, that area. I think, Nicholas, you indicated John Deere, that machine, $25 million. How many such farmers or cooperatives can handle that, okay, or can afford that? In fact, it becomes agriculture more expensive. On the other hand, here the focus is on how do we design these all different components so that even if you there's a small company, startups, they can actually work with us and bringing the solutions, and those solutions can be actually converted to AI as a service. So can a farmer actually get it, the entire service, I'll mention later on, for a $9.99 per month? That will be much more affordable. So the so the farmer can actually try to utilize and see the benefits of the AI. So that is the overall goal here. So I'll talk about that, and then I'll also discuss like how to get engaged. So if you take a look at the computing over the last 3 decades, I mean, since 1975, we started with the old scientific computing, which is still continuing. In 2000, the big data analytics came. So both the computing and the data got together. And then 2010, it is the AI wave which came. But now what is happening is, I think this is, I'm taking the things from Pete. He has been talking about this computing continuum for many, many years. And these days it is becoming very practical. So the left-hand side, if you see the traditional, okay, so you talk about HPC, big data and AI, they are like HPC systems, data centers, you have to move the data there and then perform the operation. But the right-hand side, if you see, in modern world, the data is no longer restricted to only file system. It's coming from sensors, it is coming from drones. You need to take dynamic decisions. And then the question is like, where you do the computation, how you send the data, all these things have to be designed properly for the end-to-end solutions to work. So that is the kind of the computing continuum we are focusing here. So one of the examples is actually in our institute, matching with this computing continuum is digital agriculture, okay? So Nicholas gave a lot of examples. I mean, just like think of a farmer, the traditional way, I mean, let's say in a farming season, you find that there have been diseases in the field. So how automatically can you find it out, okay? Can really a drone help? You fly a drone. Drone can actually use AI models and give the information with a fraction of a second saying, look, in this field, in this area, disease 1 is there. So you have to spray pesticide 1. Or the time of the harvest. I think, again, Nicholas made the point. I mean, if I delay the harvest by 1 day or make it by 1 more day, depending on what is happening in the world, I can make money or lose money. So these days, farmers don't have that knowledge. Can we actually provide them those kind of a knowledge in a very, with a small kind of a service kind of thing? So that's what we'll see how we are trying to achieve. So the other one is like we have 3 such applications we have taken. One is AI agriculture. Another is the supply chain management, logistics. So you talked about food wastage. Even though, like, let's say all of a sudden, you know, in the California, you see suddenly a fire has come or some earthquake has happened or some hurricane is approaching in the East Coast. Within very quick, like within a few hours, how do you make that information being available to all the logistics companies so that they can avoid that area? Or even a grocery store can quickly find out what do I need to order more for the next 24 hours. So all these things, we want to give the AI to the end users who are not like computer scientists. Okay, so that is the kind of the goal. And the third one is animal ecology, which is very much related to how the animals are behaving, how the animals are roaming, how impact it has on the climate, the conservation, those kind of things. But today I'll mostly stick to the digital agriculture. So this is kind of the examples, you know, like I started with digital agriculture, but the same, that computing continuum, you will see like a smart city, smart manufacturing, transportation, real-time surveillance, even in the medicine. Okay, now in the field, if you see, go to any hospital, I'm starting from an instrument. I mean, they take a blood sample. They're taking it through some kind of like a pathology, or you go through MRI. There's so many instruments. And in the end, it's the doctor who is looking at it and taking a decision. Sometimes it takes like, I'm sure we would have gone, right? We give the samples, you are anxiously waiting for 48 hours to see what your results are. Can we really try to make it much more faster? In like few minutes, you should be able to get your results kind of things. And can we bring AI into those kind of domains? So that is the broad objective here, to design the next generation intelligent cyber infrastructure for this computing continuum with heterogeneous resources. So when I talk about heterogeneous resources, it's not just CPUs and GPUs. Think of the arrays of devices, edge devices. There are so many different drones, so many different sensors. So they also have to be a part of the system, the computing continuum. So we need to have, like, not only understand their compute characteristics, the communication characteristics, the performance characteristics, and build this entire pipeline so that they all work in a seamless manner. And what we want to do it also, that is also another our objective, because if we want to democratize the AI, we also want it to make it plug and play. Okay, so that means anybody just like the Lego boxes, you want to provide the building blocks, but then anybody can actually utilize those. When I say anybody, like some entrepreneur or some students or researchers or companies can actually put them together in a very easy manner to have the complete solution. So they don't have to reinvent each and everything. And this is where we want to have our stakeholders and solve the societal challenges. So here I have a short video, 3 minutes video. So let me play it. So that will give you the little bit more motivation of this institute.
A policymaker wants to know how land use policies will affect a region's biodiversity. A farmer is concerned about how new weather patterns will affect crop yield, while food distributors and public health officials are concerned with how supply chain disruptions will affect deliveries of nutritious foods to communities. Current technology can provide data and models to tackle grand challenges such as biodiversity, conservation, and agricultural and food system resilience. But it still lacks the infrastructure to link across data and models seamlessly to answer complex questions from diverse stakeholders' perspectives. Even AI experts are challenged to create standardized solutions across domains because a standardized cyber infrastructure integration with AI just doesn't exist. Enter ICICLE, intelligent cyber infrastructure with computational learning in the environment. ICICLE is an institute dedicated to building a national AI-driven computational infrastructure that functions as a utility, much like our electricity, water, and transportation infrastructure. This new utility will enable the delivery of AI to end users with the flick of a switch, enlightening solutions for imminent problems of national, regional, and local importance. ICICLE will provide an operational rationale and framework for a cyber infrastructure that delivers wide and easy access to smart computing, plus a conversational interface that allows stakeholders from diverse domains to ask questions and receive answers informed by currently available data and knowledge. For example, food distributors, emergency food agency managers, and logistics company executives might ask, which food supply chains will likely be affected by an approaching storm? The ICICLE conversation agent might respond with, I will predict future states of your regional supply chain under forecasted weather scenarios and evaluate alternative scenarios. Okay? Upon confirmation, ICICLE would then retrieve satellite data on weather, connect to weather forecast models, acquire inventory data for food producers, processors, distributors, transportation networks, wholesalers, and retailers throughout the region. Use AI models to forecast supply chain conditions from a baseline, and alternative logistics that maintain consistent food supply for vulnerable populations, and estimate supply chain disruptions based on historical and current data from other locations, mindful of privacy. ICICLE will go even further by accessing high-performance computing centers to backcast and learn how reconfigured landscape-scale precision agricultural production and distribution systems could integrate with alternative supply chain infrastructure to avoid similar future disruptions. Using an orchestra of smart cyber infrastructure elements, ICICLE produces a symphonic answer that improves outcomes for diverse stakeholders. ICICLE holds the potential to transform today's AI landscape from a series of fragmented tools for use by a few to one where democratized AI and integrated plug-and-play architecture empower diverse end users with knowledge and data flows that are science-based, traceable, transparent, reusable, and trustworthy. Introducing AI for CI for AI. AI for everyone.
So this is the computing continuum I was talking about. So I indicated we have 3 of these use-inspired science domains: digital agriculture, smart food sets, and animal ecology. And this is what the ICICLE is talking. How do we design the cyber infrastructure? So this is a lot of people are involved here. OSU is the lead and the overall PI. But if you see here, this is like the US map. We have coast to coast, RPI, Delaware, Case Western Reserve, Ohio Supercomputer Center, Indiana, Wisconsin, Madison, Iowa State, TAC, University of Utah, San Diego Supercomputer Center, UC Davis, and IC Foods. And so broadly, we have like 14 different organizations. There are 33 faculty, 41 staffs, a bunch of students. So almost it is like 150 members team who are working together. And then all these are like the different collaborators, including I'll be talking about like some of those agriculture like CNS and also those who actually design the tractors and all. So we are interacting with that. So in fact, we have also gone global. Since we started it, we actually got some joint funding from Government of India. So we have started actually projects because the digital agriculture, the problem is everywhere. The solutions need not be identical. I mean, so let's say in US, you are focusing on soybean or wheat, but in Indian context, you have to worry about potatoes or onions, okay? So how those AI-based solutions can actually move across these different crops? That is also another challenge we are looking. And we are very fortunate to have a very talented external advisory board. And here we have Dan and Eva. Thanks to both of you. I've been continuously getting a lot of advice. So these are our external advisory board members. So we started in November 1st, 2021. So we are just into the 27 months of the project. So it's a 5 years project, and we have started like coming up with solutions. So first, let me give you the very broad research challenge. So this is how our overall things look like. If you listen to this video, within the system, like in the end, we want to, like anybody here, we can think of a farmer or a cooperative or a shop manager. They also want to just interact with the system, and that through conversational AI. So that is our end goal. Okay, so that's how we reduce the barrier so that actually more and more people can start using it, those who are not experienced with AI and computer science. But behind the scene, so these are actually the research development components. I'll go into more details. These are like the foundational systems AI. This is the cyber infrastructure for AI. This is something new. I think we also had a few talks. I'll go into details. AI for CI. Okay. And then we have software architecture. We also have explainability, visual analytics, and also important is privacy, accountability, and data integrity. And all these things, we are actually doing co-designing with user-inspired science cases. So in fact, in our team, not everybody is computer scientist. We have actually faculty from agriculture, faculty from veterinary schools, faculty from like a dairy distribution. So these are the people, they are the actual working with their end users. Okay, so there is a multi-layered dialogue which is going on between us to them, our non-CS colleagues, and to the end users. So let's start with the foundational system. So this is an NSF-AI Institute. So they want fundamental advances in the AI itself. So these are the kind of the different thrusts we have. And one important thing is the knowledge graphs. So in any of these domains, whatever I indicated, if you go down, you will see that you have to build knowledge graphs and with a lot of heterogeneity. And this could be like a multi-million size of the graphs, okay? And to bring their appropriate ontologies, okay? So that you can actually then build your AI model on top of that. So that is very first step. So then we have model commons. So the model commons, just as I said, like let's say very simply, we can think, I can fly a drone. Drones are so different with different characteristics, different power requirements, different capabilities of CPUs, GPUs. Instantaneously, how can I decide for this drone, it should automatically select this AI model? Okay, so that is kind of a model common. So same thing happens with data commons, like what do we want to use? Adaptive AI, this is very important because in all this computing continuum, even if let's say drone is flying, how much bandwidth you have from that drone to the base station or to the nearest cloud, okay? So depending on that, you have to select different kinds of algorithms, whether I compress it, what compression I do, should I store the images or not, or drop those? So all those things we need to make. Then federated learning is very important here because we are working on a lot of data, and then a lot of farmers and all, they don't want to share the data. So this is where the federated learning comes in, so that even without the complete access to the data through their APIs, you can actually build the models. And then, of course, we have the conversational AI. So think of like, I know we are in a chat GPT world, LLMs, but if you really go down, there is no real LLM support for digital agriculture, let's say, or even the farmers, the language they speak, and there are so many different countries, okay? So that itself is a very huge effort to make sure that a farmer can actually talk to into your iPhone with appropriate vocabulary. The second thrust is actually the CI for AI. So this is what I think is very much familiar with many people here, the cyber infrastructure. So this is where my main thing, whatever I talked earlier, like high performance computing, machine learning, deep learning all comes. Data management, that is also important. Then this edge intelligence and adaptive AI as wireless. So we have actually in our team, Iowa State, so there are faculty who are actually working on the wireless technologies. So they are bringing the fundamental advances to all these newer kinds of compression. How do you do very dynamic compression, rateless coding? So all these things are happening. And then, of course, the question is, how do we actually control and coordinate all these things? So this is something new. We had a little bit of that in yesterday, AI for CI. Okay. So CI for AI, people can understand, I am designing cyber infrastructure for AI, but the question is, while I'm trying to design the systems, can AI help me improve or optimize? Okay. So historically, if you take a look, I'll just give an example of scheduling. How many of you have done job scheduling or known about this? I'm sure many of you are, right? So these are all based on algorithms, okay? 30 years of research have happened on algorithms, okay? They're very, very complicated algorithms. Those have been incorporated into like a slurm, PBS, and all those things which we use. But if you now think of like you are trying to start a drone session, you don't want that algorithms to be run, okay? So the question is, can all those data, whatever we have, like how the scheduling works, while the drone is starting to fly, it needs to find out based on the available bandwidth and the cloud availability, and then the cost of the cloud. Should I push the data to a cloud or to an HPC center? So that is what I'm talking about, the scheduling. Now the question is, can those algorithms-based solutions be converted into AI-based solutions? So when I say AI-based solutions, I can take all those data and build a model, okay, on the scheduling. So think of like a distributed neural network model, and I have all the scheduling insight and then see what works, what doesn't work. And if I can build a model like that, then what I need to do is it just does the inferencing. Once the drone starts flying, it exactly gets the data from saying, okay, this is the cloud, these are the prices, this is the availability of all the supercomputing center, I need this much data. So use it as an inference, and then you get the answer quick. So this is just an example. You can think of performance optimization. We heard that yesterday afternoon. So a lot of these traditional things can now be converted into AI. And that's what we saw, say, like AI for CI. And then, of course, the privacy, accountability, data integrity. This is very important in this domain because we have a lot of stakeholders like farmers, industry partners, etc., both from the digital agriculture as well as the smart food sets. So this is where we are working with a lot of people. So this is very important. And then we have also, like anytime, I'm sure all of you know, any AI solution, you need to have explainability. So we have actually strong visualization team, okay? So as the data and all is moving, so we have built like a user interaction, the data knowledge and models, it can actually visually show you how the data is moving, what kind of decision took place, so that if you're trying to challenge the answer, you should be able to actually see the workflow, the control flow, data flow, and how these results are coming. And then, of course, our co-design. Again, I just want to highlight that. So all these things we are trying to do co-designing. And then here, if you see, this is the computing continuum. So this is our ICICLE logo, but deliberately the size is actually like this. Think of like a sensors, a drone. You don't have to use memory. You don't have to use power. So what we want is it is actually a distributed software. It has to work together, but a tinier version is actually running on your drone. But a little bit middleweight version is running on your cloud, and a very heavier version is running on the supercomputer center, but they are all working together, kind of things. And then here we are leveraging at the TAC, there is a project called TAPIS. It has been there for many years. They have been funded by NSF. So instead of building scratch the entire software stack from zero, we are leveraging the TAC, the TAPIS framework. So it is being built on top of TAPIS. So it has a lot of different kinds of authentication, the scheduling and all. And then we are trying to build all these color-coded boxes. Are like some of them are being enhanced, some of them are being introduced new. to make this computing continue together. And then, of course, there's the National Science Foundation project. I mean, so even though it's a research, but we also have a lot of focus on the diversity, inclusion, BPC, this what we call like a broader impacts backbone network. And this is very nice in the sense, as I said earlier, we have a very large team, 150 people. So in fact, what the approach we are taking, all these BBIN principles, first we apply it to ourselves. If things work within a team of 150 people, there is a higher confidence that it will work outside. Okay, so that is the kind of the approach we are taking to make sure that this we are not just thinking or talking all this in a conceptual manner. So with this, let me go into details how we are trying to design these digital agriculture activities for the. So this is like the team is still growing. These are some, as you can see, they are all different universities and places. So what we are trying to go here, and I'll show you some concrete example, like how does the cyber infrastructure for digital agriculture look like? I mean, I talked about this drone, but in the next 10 to 12 slides, I'll really go into down. So how do you build this piece by piece? Okay, and then so that you can put them together like a plug and play solution I talked about. And so that you can actually, that will help a lot of digital agriculture stakeholders, and then it can actually be transformative and trying to solve the digital agriculture solution for the next 10, 20 years. So these are the kind of things, okay? So first, think of like a very naive, let's say you don't know anything. I gave an example of this drone, okay? So let's say the drone is flying and the drone is trying to give the farmer saying what part of the field has what disease, okay? But before that, if you divide that problem into small problems, first you will see from the application domain, what kind of crop it is, what kind of diseases are happening, how do I take that information, okay, and build an AI model. So that is like a data labeling challenge. Then how do I do the learning on top of it? So to build the model. And once I build the model, then that model again, I need to see that, okay, can it fit into a drone or can it fit into an edge device? And if not, we need to come up with better solutions, okay? Use some different quantization, reduce the power requirement so that I can actually deploy it. And then the question is, once I am ready, again, the drone, how do I fly the drone? If it is a very big field, should I fly only one drone? Should I fly some 10 drones? Can they work in parallel? Can I take parallel computing to the drone's level? Okay, so that can work in together. And then the question is, how do I put all these things, components together? Okay, so we have dedicated teams are working on all these different angles. So let me go into each one of these. So the first one is application domain challenge. Okay, even though we say the job is easy, when we wrote the proposal, we said, this will be very easy, we can do it. But once we start realizing and implementing, so think of like this, there are all different data you can get. Residue cover on soil surface, soil aggregate size, how the wheat development takes place, okay, or non-uniform emergence, nitrogen efficiency. There are different kinds of the pests can affect this, like corn leaf aphid. There's a Mexican beetle defoliation. So all these are real practical things. Now you need a lot of images and the knowledge associated with this to identify. Okay, so just to give a small example, I'm sure if you have a rose plant at your home, every year you shall see some diseases coming. Okay, they're not the same. Okay, and then of course every time, at least in my home, we say, this we didn't see last year or last 10 years. So what is new? It depends on the climate. It depends on the weather. Okay, so same thing is happening. So here we need a lot of domain knowledge, and that's what we are working. My colleagues who are in the agriculture department are trying to actually provide us this kind of information. Okay, without that information, we cannot do anything. But then what happens associated with this? Now the next thing is the data labeling. That also becomes a big challenge. Somebody has to give you an image and also level saying, okay, this is the disease X, or this is all these examples I talked about, am I right? The previous slide, like a different soil moisture content, or like how do you detect all these corns, are all they growing in an appropriate manner or not? So there are fundamental techniques. And this data sometimes can become millions of these images. And data labeling is itself a big challenge. And sometimes even you don't have all this data. Okay. So in fact, this is not only in the digital agriculture field. In this whole AI field, data labeling is a big challenge now. Okay. And if some of you don't know, I think just like, in the outsourcing, you must have heard of that, like in US at least, in the early 90s, a lot of things got outsourced to India and other places, okay, the back office kind of things. Now it is happening. The AI world is actually being outsourced. Labeling part. A lot of people in India are just continuously being paid to take an image and then put the appropriate labels. Okay, so unless you have that, you cannot actually run the training. But then the question is, even though you spend a lot of money, this is like most of the AI people know, like a supervised learning. I need all this to be labeled, then only I can make the decision. This is not practical. It is very expensive. So then the question comes that can I actually do some other alternative like semi-supervised learning? Okay, so that means given a soft set of data, can I actually build my neural network model, which will be much more accurate and can run faster? So that's what we have developed, like a SSL, we call it like a semi-supervised learning. So that might be, I'll show you in the next few slides, 1% data, 2% images. And if they have been labeled correctly, we can take that information and all the other data we passed as unlabeled, but still we get some good answer, okay? And that's what we have done here. We call it like a harvest, high-performance artificial vision framework for experts labeling using semi-supervised training. So in this case, you can actually, we're trying to build it as like a service. In fact, an internal version is already running in my lab. And gradually, actually, we are working to deploy it in the Hawaii Supercomputer Center, San Diego Supercomputer Center, some of our collaborator centers. So once it runs, we call it like a bring your own data, BYOD, okay? Instead of a beer, you just bring your own data. And then you trigger this, and this entire pipeline, it will run. And it will give you the model in the end, okay? And we don't want to claim any ownership of that. We just have this CyberInfrastructure. You have your ownership on the data and also on the final model. Okay? And we developed this using like a Hawaii Supercomputer Center, and a lot of supercomputer centers use open on demand. So we have a complete solution here with unsupervised trainer, labeler, inferencing engine, going through the standard PyTorch, and linking with our MPI library or Nickel library, CUDA library, can run on all the GPU systems. So you don't have to worry about all these things. So this is the complete system what we have developed just for this labeling. And so now if you see the accuracy, so these are actually data. We presented this just 2 months back in the IEEE Big Data Conference. So here we took like a different kinds of data sets. So it's the plant stress identification for protecting crops through the growing season. So we had like a data set. One is a corn crops, around kind of 1,000 samples, then soybean crops. And we are able to, instead of like almost 10,000, we just use 80 labeled samples, okay, for class. And then here you can see like we are able to get 97-93% accuracy, okay. So we are cutting down significantly the training time using this kind of semi-supervised learning. And then we are also able to scale that into a number of different GPUs. So then once we have the model, let's say you get all the data, now you need to see that model. What is the size of the model? What is the kind of the power requirement for that model to run when you are trying to do inferencing? Okay, because typically the drone will go and then the model has to fit there. Okay, so this is where we have been trying to do a very systematic way of like a various quantization techniques, integer 8, FE16, and then all these different range of DL inference frameworks, the OpenVINO, PyTorch, TF-Lite, Onyx, etc. Even going into different kinds of CPUs, Raspberry Pis. And what we did, this paper was presented at the Fog and Edge Computing last year. So here we actually demonstrated that if you use take the model, the original models, you can reduce by almost to 25% of its size using this integer 8-based model without losing any accuracy. So that means that model now becomes very practical to be deployed on your edge device. Okay, so I started with like the image, semi-supervised learning. I have the model, I have the quantization, so on. My model is ready to be deployed. But then the next question comes: how do I actually deploy the drone? So that is actually a big field. I mean, I didn't know. I thought, oh, drone is very simple. You can just fly. I mean, you have to go through this. My colleague, Professor Chris Stewart, he has been working in this area for a long time. So the idea is that as I said, like let's say this is a field, you want to fly these drones, and then you can get that heat map. That is the end solution. Here, of course, it's like assuming there is only binary solutions. That means whether you have a disease or don't have a disease. But if you have 3 or 4 different kinds of diseases, you can color code. That's what the farmer wants in the end, okay, out of all this entire thing. And so here what he has done, and we want to do it in a very finer granularity. So using all the unmanned aerial vehicles, and it flies low, almost like a 15 feet above the ground, and almost like a 1 pixel millimeter level granularity. He has actually shown even you can actually detect the beetles on the leaves, like because you are running on a 15 feet level, so that you can actually zoom in and find out what exact kind of diseases are happening. And we have a very fortunate to have actually Ohio State University, is like a land grant university. So we have a lot of connections with the farms. So one of these farms actually works out with us very collaboratively. And he has been running it. And there are 2 components, actually. I'll show you later on, but this is like he has a software pilot and then the OpenPass. So the OpenPass is actually a Kubernetes-based component based on his software pilot, and these are all released. So if you have a laptop and a drone with you, you can actually download all these things. And in 10 minutes, you can configure it and fly a session. Okay, that's how we are trying to enable or democratize the solutions. And then the bigger question comes, like let's say there is a very big field. If you just fly a drone, it may take like 5 hours to get all this information, but then the drone doesn't have battery life up to 5 hours. So then the question is, okay, can I now fly tens of such drones? And this is where we are taking parallel computing to really to the edges. Okay, so these drones actually, once you launch them, they actually are communicating with each other. And exactly saying, okay, I run this part, you run this part, and whatever information I'm sharing with them. So these are the algorithms they're using to come up with this final heat map. Okay, and so then what you can do is actually give this to the farm. But then this pipeline, so this is where we are. Of course, we want to convert the complete things. Like I started with these crop health issues, data harvesting, HPC for ag AI. Then this is the computing continuum. But we need to link it to the end tractors and all. So at this time, we have reserves up to a farmer or a cooperative. They can get the solution. And then the question is, okay, do you do manual spreading of your fertilizers or anything, pesticides, or we want to really connect it with the tractors, like this John Deere or CNH, a lot of these people who are making these tractors, so we are talking to them. So there is a chicken and egg problem, as you said, like John Deere is making big amount of money, $20 million of each equipment. And then the question is, okay, if they start adopting our solutions, I mean, these are open source solutions, okay? And this is, of course, one of the mandate from the National Science Foundation. We need to make all these things available, democratize AI. So we'll see how that field will come out, because there is a lot of business-oriented decisions which are beyond our control, okay? But the whole idea is that any other farm or anybody else can take our solution, have a competing solutions to John Deere, which will be like $1,000 per piece solution. You don't need $1 million, okay? So this is where I will see that the solutions actually will go to the end devices. And then all these things, just like if you think I said, like the farmer will just trigger from here. Everything else, he or she doesn't have to know anything, or even talk saying, I want a sweep of my field tomorrow to find out what diseases had happened. Okay. And then if there are some drone services are available, they will actually fly and run all these things, our software, and give the solutions to the farm. That's all. We want to make it as easy or a low barrier point kind of thing so that the farmers can use. So then we are going with one is our AI Institute. There are other AI institutes. There are 3 more institutes who have also focused on agriculture. We are talking to each other. Our focus is the CyberInfrastructure. But then each of these AI institutes have a little bit different. For example, Ag-Ed, this is from University of Washington. They are looking how do you harvest? Like how do the robots actually go and pluck? If it's an apple, how do you know that it is ripe? Or is the grape, is it ready to be taken? Okay. So because there is a big labor intensive process, just harvesting the crops. So this is where we are talking, like whatever we have developed the cyber infrastructure, can they actually utilize that? Okay? So like this, we are building consortium kind of things within all the AI institutes. And I indicated like we are talking about the CNH Industrial. There is another company called TCS, some of you know from India. They have actually been working within India. You mentioned about this. Of course, they have given a big contract to all these companies, but these companies, TCS, they actually work with a lot of cooperatives all over the India. So this is where we are trying to reach. At a cooperatives level, if we can give them the solutions, then the cooperative people can push it to the farmers. Okay, so that more and more people will be using it. And then I talked about this collaboration with the TH Mumbai. Yes. So then as we are working on, if you go to our site here, go under software. So component by components, we have started releasing. Okay, so every 4 months, we have a target. So there are dedicated team within our things. They take the solution, integrate, test, and then make it available. So like this, you can see like all this digital agriculture I talked here, different kinds of simulators, in-field helper. So we are not waiting until the 5 years to be over and then give a solution. We are trying to open it up so that people can actually work with us and test it. We can actually work with them to make the solutions more robust. So like this, every 4 months, you will see some solutions come up. So then let me try to finish this, how to get engaged. So this is again an NSF-funded project. As you said, Nicholas, or in the mornings, I think I see a lot of work activities taking place in New Zealand in these kind of things. So of course, the first thing is like the software. If people want to use them, these are all free. Please feel free to download. You can subscribe to our mailing list. You get periodic information on what is happening. We also have a lot of, you can be a part of the ICICLE, either as a student or visiting research fellow, academic collaborator, industry partner, stakeholder roundtable. So we have a page. If you just go there and you can take a look, there are different options. Please submit a form, and then one of our team members will actually go and then contact you. We can have a follow-up discussion and see at what level the engagement will be fruitful. Okay. So with this, let me conclude here. As I said, like our broad objective is to really design the next generation cyber infrastructure through co-designing with user-inspired science domains. At this time, we have only these 3. I didn't go into details. So same thing we are trying to do food supply chain management. We have actually solutions available there from like the California, our IC Food and UC Davis. They have a very large connections to all the different agriculture producers and consumers. And we have actually provided very nice tools for them. Within minutes, you can actually find out, say, okay, I'm looking for this kind of product. Who are all the manufacturers? Where they're working on? And if suddenly let's say I gave them an example of a freeway having a fire, very quickly you can reorganize themselves and then continuous do the transportation, same thing we are doing with animal ecology. But our whole idea is that once we validate our solutions on these 3 things, these are all very similar. We can take our solutions to health and medicine, environment, collaboration, mobility, in general, AI for good. So with this, let me conclude here. Our broad objective again is to really having a global leadership for both computing and AI. That is our focus. That is the responsibilities given to us by National Science Foundation. And we want to be like looking forward like a 2035 or 2040. We want to make sure that the framework, whatever we are designing, the reference architectures we are designing, will actually help to design these kind of systems for the next 20 years. And at the same time, we also want to be collaborative and sustainable and also inclusive kind of things. And of course, there is a big thing. I didn't go into details. We have that Bibin group is actually, we are actually working with a lot of high school students, K-12 students, to tell them, look, these fields are very exciting. They know about AI, but how do you translate that into to real concrete examples so that they get very excited and they get to come to these kind of schools, colleges, so that they themselves will be the designers at some time in another 5 years. So with this, I'd like to give thanks. I mean, it's a very big team. As I said, I'm just here to talk, but they do all the hard work behind the scenes. So I'd like to salute all of them. And with this, thank you. And I'll be very happy to take questions.